Today we'll introduce some really basic modular arithmetic. This is very, very important in computer science and pretty much anything to do with discrete math, so this is probably like the most important lesson in the course besides proofs, as far as a single unit of information that you're going to use all the time. So, I should probably define it for you. If a and b are integers, and m is a positive integer, then a is equal to b modulo m if m divides a minus b. So this is a little bit sort of interesting, but let's take some arbitrary numbers here. We know that 3 divides 6. So we can say that 3 divides, let's do 18 minus 12. So what we can say here is that 12 is equal to 18 mod 3. And the question is, what are the applications of this? And I should say also that 18 is equal to 12 mod 3 if I was being really specific with the example. Alright, let's take a look at something. Does 53 equal 17 mod 3? So let's take a look at this. We have, does 3 divide 53 minus 17? That is to say, does 3 divide 36? And of course we know that. Well, does 53 equal 14 mod 3? And if we do some arithmetic, we find out that yes, it does. What about 11 mod 3? Okay, so we keep going down, and we keep going down. But does that mean that 17 mod 3 is equal to 14 mod 3? And, well, that's kind of an interesting question. Do these two numbers, mod 3, equal each other? And it seems, by transitivity, that, yeah, well, of course they are. But what does that really mean? What sort of relationship do we have here if we know that two numbers mod each other? In fact, what we see here is that this 3 is the difference between these two numbers. So what does that mean? Well, we call these numbers congruencies, and they are actually equivalence classes. So let's take an example in Mod 4. Well, to set up equivalence classes for modular arithmetic, what we do is if we have mod n, we set up equivalence classes for 0 all the way up to n minus 1. So you can see here that we have 0, 1, 3. I should probably write a 2 in there. And these are the 4 equivalence classes we have. Now, here's the thing. When we go back to this example, and we have mod 3, eventually this will lead to 8, 5, 2, and then it stops. It stops at 2. In fact, if you've been paying attention and thinking about this, you'll see that this final number it stops at is actually the remainder. So really, what these equivalence classes are they are the remainder of the division of, say in this example we have 4, so every number divided by 4 that has a remainder of 0 is going to be the big number representing the equivalence class. So you can see here that this set 0 will contain the numbers -4, 0, 4, 8, 12, 16, so on and so forth. And then with number 1, well, we have 1 divided by 4, that's going to have remainder 1. If we have 5 divided by 4, well, this is going to be 4 times 1 plus 1, which is our remainder 1 here. So what about the 2? Well, of course it goes from infinity, and we'll see here that this is -2, 2, 6, 10, so on and so forth. In fact, if we take 10, this is equal to 4 times 2 plus 2. So again, we have the remainder 2 for this equivalence class. And for 3, this should be pretty easy to generate now. -1, 3, 7, 11, so on and so forth. And if we take the number, let's take 15, we see this as 4 times 3 plus 3, which is a good representation of the equivalence class. Of course, what we've seen before is that with equivalence classes, we know that the equivalence class of 3 in this case is going to equal the equivalence class of 7, since either they're exactly identical or not the same at all. And because we can subtract 4 from 7, it reduces to 3, and we use the smallest number usually to represent the equivalence class. So here's a question. What else do you notice about these wonderful, wonderful things here? These equations we have. So there's something interesting other than the remainder that I pointed out, and in fact there should be, and you'll notice that the number in our formula, a is equal to dq plus r, this d is really going to be the modulo number that we're working in. So if we have, for instance, mod n, this is going to be a is equal to nq plus r, and of course this r right here, this determines the equivalence class. So that was basic modular arithmetic. Hopefully that wasn't too bad. Again, this isn't really talked about too much in discrete math 1. Its applications are pretty much the division algorithm and extensions of it, but it's still kind of important to realize. In fact, a lot of the times there's a really cool chart that you can draw with these numbers. So we take mod, I don't know, let's say 4, then we write down all of the equivalence classes here. So we have 1, 2, and 3. And then what we do is we just start wrapping numbers around. So instead of going all the way up to, say, 10 in a number line, after we get to 3, we just wrap around and continue going. And what's interesting here is that if we take a look at, say, the number 9, and we say, okay, what is 9 mod 4 equivalent to? Well, this is going to be in the 1 equivalence class, which also means it's in the 5 equivalence class, it's in the 9 equivalence class, it's in the 13 equivalence class. It's in all of those, but they're all the same. So you can keep doing this forever and ever until you get to whatever number you want to go to. Of course, infinity is not a number, but again, it's just to make a point. So that's how you deal with modular arithmetic. There are a lot of proofs with this too, which of course you can do with the definition I gave here, but I don't have any proofs for you to do. If you take a look at the book of proof, I believe there's a nice chapter on modular arithmetic. I'm not using that for these slides. I've stopped using that book since the first part of the course as soon as I got to counting, because their counting section was really mediocre. But that's modular arithmetic. If you have any questions, feel free to leave them in the comments and I'll get to them as quickly as possible. And that is all.